Video 54. Prove by induction that sigma k equal to 1 to n k squared is equal to n into n plus 1 into 2n plus 1 by 6. Sigma k squared means 1 squared plus 2 squared plus n squared. Sum of these squares of first n natural numbers. Proof. Let P of n be the statement that is 1 squared plus 2 squared plus etc. plus n squared. Sum of the squares of first n natural numbers n into n plus 1 into 2n plus 1 by 6. Then we have to list out what is P of 1. You see there are n terms here. In P of 1 there will be only one term on the left side. In P of n this is equal to, before equal to we have n terms. In P of 1 before equal to only one term. Right side 1 into 1 plus 1 into 2 into 1 plus 1 by 6. P of k is 1 squared plus 2 squared plus etc. plus k squared is equal to n is k into k plus 1 into 2k plus 1 by 6. P of k plus 1 is 1 squared plus 2 squared plus etc. plus ending with k plus 1 whole squared. This k is k plus 1. K plus 1 is k plus 2 into 2 into k plus 1 is 2k plus 2 plus 1 2k plus 3 by 6. So this replace k by k plus 1. 2k 2 into k plus 1 means 2k plus 2. This one 3. This one is 3. This is 1. Now we have to go for basic step. So what is LHS of P of 1? Here we take n is greater than or equal to 1. LHS of P of 1 is equal to 1 squared, which is 1. RHS of P of 1 is equal to 1 into 1 plus 1 into 2 plus 1 by 6, which is 2 into 3 by 6, which is 1. Therefore, LHS of P of 1 equal to RHS of P of 1. Therefore, the conclusion is, therefore, P of 1 is true. Now we have to go to induction step. Induction step. Assume that P of k is true. That is, P of k is 1 squared plus 2 squared plus etc. up to k squared is equal to k into k plus 1 into 2k plus 1 by 6. Equation number 1. This we are assuming. Now LHS of P of k plus 1 is equal to 1 squared plus 2 squared plus etc. plus ending with k plus 1 the whole squared, which is 1 squared plus 2 squared ending with k plus 1 whole squared. The previous term is k squared. 1 squared to k plus, this 1 squared to k squared is given by equation number 1. K into k plus 1 into 2k plus 1 by 6 plus this term k plus 1 the whole squared, by equation number 1. So now we can take k plus 1 common. K plus 1 into k into 2k plus 1 by 6 plus k plus 1. Taking LCM, k plus 1 into 6 LCM. This is 2k squared plus k plus 6 into k is 6k plus 6, which is equal to k plus 1 into 2k squared plus 6k plus k 7k plus 6 whole divided by 6. This is k plus 1 into, we can factorize 2 6 or 12. So factorization gives 2 6 or 12, 7 means 4 3. So this we have to factorize it as 2k squared plus 4k plus 3k plus 6, which is equal to 2k into, we are factorizing only this k plus 2 plus 3 into k plus 2, which is equal to k plus 2 into 2k plus 3. So that factorized formula we put here, k plus 2 into 2k plus 3 whole divided by 6. This is our RHS of pk plus 1. Therefore, what is the conclusion now? Therefore, p of k plus 1 is true whenever p of k is true. Therefore, p of k plus 1 is true if p of k is true. This statement we call it as 2. P of 1 is true. Already we proved LHS of P of 1 equal to RHS of P of 1. P of 1 is true. Therefore, by 2, whenever P of k is true, for the next integer it is true. P of 1 is true. Therefore, 1 plus 1 P of 2 is true. P of 2 is true. Therefore, by 2, the next integer 2 plus 1 P of 3 is true, etc. So continuing like this, etc. Therefore, by induction, P of n is true for any positive integer. That is what we want to prove, because the given statement is taken as P of n. Therefore, we need to prove P of n is true for any positive integer n.